4 light-years sounds close until distance is measured in human terms. At Voyager 1's speed, the nearest star would still be roughly 74,000 years away. Push a spacecraft to 1/5 the speed of light, and the crossing shrinks to decades, but then dust grains become dangerous projectiles. Radiation accumulates, communication falls years behind, and even stopping at Alpha Centauri becomes a problem nearly as difficult as getting there. If calm journeys through extreme science are worth returning to, a like subscription or share helps calm space science continue creating them. And wherever this video has found you, leave a comment with your city or country and the time on your clock, whether you're settling down for sleep, studying, working, or simply listening in a quiet room. Thank you for spending part of your time here. The Sun is still behind us. Alpha Centauri is barely a point ahead, and the first boundary of interstellar space is waiting. Proxima Centauri is often described as the nearest star to the Sun, and the phrase sounds almost comforting. Nearest suggests proximity, a destination placed just beyond familiar territory. Yet the number attached to that description changes the meaning completely. Proxima Centauri lies about 4.24 light-years away, while the brighter Alpha Centauri A and Alpha Centauri B are slightly farther, at roughly 4.37 light-years. A light-year is not a measure of time, but of distance the span light crosses in 1 year, while moving at almost 300,000 kilometers every second. 1 light-year is therefore close to 9.5 trillion kilometers. 4 light-years are not simply 4 times something large. They're a distance so far outside ordinary experience that almost every comparison begins to break down. Even the language of astronomy, built to handle enormous scales, has to compress it into a single convenient unit before the number becomes manageable. The Earth is already separated from the Sun by a distance that once seemed almost beyond measurement. Light needs a little more than 8 minutes to cross that gap. The distance is about 150 million kilometers, and modern spacecraft spend months or years crossing comparable stretches of the solar system. Neptune, the outermost major planet, circles the Sun at an average distance of roughly 4.5 billion kilometers. Sunlight takes a little more than 4 hours to reach it. From Earth, Neptune belongs to the remote edge of the planetary system, a world so distant that only one spacecraft has ever passed close by. Yet compared with Alpha Centauri, Neptune is almost beside the Sun. The distance from the Sun to Proxima Centauri is thousands of times greater than the distance from the Sun to Neptune. A spacecraft could cross the entire width of the planetary region again and again, and still have covered only a small fraction of the interstellar gulf. That contrast is easier to feel when the solar system is reduced in scale. If the distance from Earth to the Sun were compressed to 1 meter, Neptune would orbit at roughly 30 meters from the Sun. The planetary system would fit within the dimensions of a large building or a small field. On the same scale, Proxima Centauri would not be a little farther beyond Neptune. It would be hundreds of kilometers away. The nearest star would lie beyond cities, beyond local horizons, separated from the miniature solar system by an emptiness far larger than the entire model that came before it. The planets occupy a relatively compact island around the Sun. The next star system is not simply the next object past the edge. It belongs to another island, divided from ours by a distance that dominates the map. The same problem appears if distance is measured in travel time. A beam of light leaves Earth, passes the Moon in a little more than 1 second, reaches the Sun in a little more than 8 minutes, and crosses the orbit of Neptune in a few hours. After that, the beam continues outward into a region with no planets, no bright landmarks, and no convenient markers of progress. A full day passes, then a week, then a month. Even after a year, light has completed only about 1/4 of the journey to Proxima Centauri. More than 4 years must pass before the same beam reaches the nearest stellar system. Nothing built by humanity moves remotely that fast. The light year hides this severity because it uses the fastest thing in nature as its ruler. There is another way to see the scale. The Earth travels around the Sun at nearly 30 kilometers every second, an orbital speed already difficult to reconcile with the stillness of ordinary life. At that speed, a traveller moving in a straight line toward Proxima Centauri would still need tens of thousands of years to arrive. The problem is not that Alpha Centauri is unusually remote. The problem is that interstellar space is naturally immense. The architecture of the galaxy places stars at distances that dwarf the dimensions of their own planetary systems. The Sun is a sphere little under 1.5 million kilometers wide, yet the space separating it from its nearest stellar neighbor is tens of millions of times larger than the Sun itself. Stars may appear crowded in the night sky because distance collapses onto a flat view from Earth, but in 3 dimensions they are separated by enormous volumes of darkness. This has a quiet consequence for every imagined interstellar mission. Before propulsion, shielding, navigation, or survival are considered, the first obstacle is geometry. The destination is close only in a galactic sense within the Milky Way, whose disk stretches across roughly 100,000 light-years. A journey of a little more than 4 light-years is almost microscopic. But human engineering is not measured against the diameter of the galaxy. It is measured against lifetimes, energy budgets, material limits, and the speeds that machines can actually survive. A distance can be trivial on one scale and overwhelming on another, and Alpha Centauri occupies exactly the contradiction. It is the nearest possible example of interstellar travel, which also makes it the clearest demonstration of how hostile interstellar distance is to ordinary assumptions about motion. The visual appearance of the target adds to the illusion. Alpha Centauri is visible from much of the southern hemisphere as a bright point in the sky. Proxima Centauri is too faint for the unaided eye, but it belongs to the same neighbouring stellar system. Nothing in that appearance communicates distance. A star is reduced to a point because it is so far away that its physical size cannot be resolved without specialized instruments. Its brightness arrives without scale, carrying no obvious sign that the light itself began its journey years earlier. When Alpha Centauri is observed from Earth, it is seen as it was more than 4 years in the past. The present state of the system is already beyond direct knowledge. Any signal, image, or measurement crosses the same gap that a spacecraft would have to cross, only at a speed no spacecraft can match. Even the kilometre becomes awkward at these distances. Writing the journey as tens of trillions of kilometres produces a number that is technically precise but mentally weak. Human intuition is adapted to walking distances, landscapes, continents, and perhaps planetary maps. Beyond that, numbers grow faster than instinct. 1,000 kilometres can be connected to a nation. 1,000,000 kilometres can be understood through the moon and the space around it. 1,000,000,000 kilometres begins to describe the outer solar system. Tens of trillions of kilometres belong to a different category. There is no direct terrestrial analogy large enough to make the distance familiar without shrinking one scale or exaggerating another. That is why the phrase nearest star can be misleading without being wrong. Proxima Centauri really is the closest known star to the Sun. Alpha Centauri A and B really are only slightly farther away. In the stellar neighbourhood, they are next door. But the neighbourhood itself is built on dimensions that make ordinary travel almost irrelevant. Between the Sun and Alpha Centauri, there is no chain of intermediate worlds that gradually shortens the crossing. There is no natural bridge. Once the outer solar system fades behind, most of the journey is simply interstellar space, measured not in planetary separations but in fractions of a light year. The first meaning of an Alpha Centauri mission therefore has nothing to do with exotic engines or distant planets. It is the recognition that the journey begins with a scale mismatch between human machines and stellar geography. The solar system feels enormous because reaching its outer regions already consumes years and decades. Yet from the perspective of the nearest star, the whole planetary system contracts into a small patch around one ordinary sun. 4 light-years then open beyond it, a gulf so large that the familiar distances between worlds become almost negligible. Before any spacecraft can cross that gulf, it must first escape the region that has contained every human journey so far, and even that departure will prove to be only the beginning. The first stage of an interstellar journey does not begin between the stars. It begins inside the Sun's own extended domain, where planets, dust, magnetic fields, and the solar wind still define the local environment. From Earth, the solar system can seem as though it ends somewhere beyond Neptune, because Neptune is the outermost major planet and its orbit provides a familiar visual boundary. Physically, however, there is no sharp wall at the last planet. This sun influences space far beyond the planetary region, and a spacecraft heading toward Alpha Centauri would spend years crossing layers of territory that still belong, in one way or another, to the solar system. The first landmarks are comparatively familiar. Mars, Jupiter, Saturn, Uranus, and Neptune occupy orbits that become progressively wider, and a spacecraft moving outward passes through a system whose distances grow faster than intuition. Jupiter alone orbits several times farther from the Sun than Earth does. Neptune lies roughly 30 times farther from the Sun than Earth, and even after reaching that distance, the spacecraft has not entered interstellar space. Beyond Neptune lies the Kuiper Belt, a broad region containing icy bodies, dwarf planets, and remnants from the formation of the solar system. Pluto is one member of this larger population rather than a marker of the system's true edge. The Kuiper Belt extends far beyond Neptune, but even its outer regions remain deep inside the Sun's wider magnetic influence. What matters for an interstellar mission is not merely whether planets are behind it. The more meaningful boundary is created by the solar wind, a continuous flow of charged particles streaming outward from the Sun. Near Earth, this plasma moves through the solar system at hundreds of kilometers per second, carrying the Sun's magnetic field with it. As the solar wind expands, it becomes thinner, but it does not continue without resistance. The space between the stars contains its own dilute gas, plasma, magnetic fields, and energetic particles. Eventually, the outward pressure of the solar wind becomes weak enough that the surrounding interstellar medium begins to dominate. The enormous cavity carved by the Sun into that medium is called the heliosphere. For a spacecraft attempting to leave the solar system in the practical sense of entering interstellar space, crossing the outer boundary of this cavity is one of the first true thresholds. The journey toward that threshold is not simple. Long before the solar wind stops dominating, it changes character. Far from the Sun, the wind slows as it interacts with the interstellar environment. The region becomes structured by magnetic fields and populations of energetic particles that are difficult to picture as a clean sequence of shells. The outer heliosphere is dynamic, shaped both by activity from the Sun and by the motion of the solar system through the surrounding interstellar medium. The heliopause marks the boundary where the outward solar wind is no longer able to push farther in the same way, and the interstellar environment takes over. Crossing it is a more physically meaningful transition than merely passing the orbit of the outermost planet. Voyager 1 provides the clearest real example of how long such an escape can take. Launched in the late 1970s, the spacecraft used encounters with the giant planets to gain speed and was placed on a trajectory carrying it outward from the Sun. It passed Jupiter and Saturn quickly by interplanetary standards, But after those encounters, the journey became one of patient outward motion. Years became decades. Long after its planetary mission had ended, Voyager 1 continued measuring particles, fields, and radiation while moving through regions that no previous spacecraft had sampled directly. Only more than 3 decades after launch did it cross the heliopause and enter the local interstellar medium. That achievement is often described as humanity's first entry into interstellar space, but the phrase can conceal how modest the distance remains compared with the journey to another star. Voyager 1 had travelled an extraordinary distance by human standards, yet it had crossed only a tiny fraction of the separation between the Sun and Alpha Centauri. The comparison is important because the heliopause feels like an ending. It is the outer border of the Sun's solar wind bubble, and crossing it changes the environment around the spacecraft in a measurable way. The density and character of charged particles change. The influence of the interstellar medium becomes clearer. Galactic cosmic rays can penetrate more freely. The magnetic environment is no longer governed in quite the same way by the outward flow of the solar wind. For the spacecraft, however, this is not the completion of escape so much as the end of the opening movement. The planets are far behind. Sunlight has weakened enormously, and the familiar architecture of the solar system has nearly disappeared from immediate experience. But the nearest star is still almost the entire journey away. There is also a deeper complication in deciding where the solar system truly ends. The Sun's gravity reaches far beyond the heliopause. Objects thought to occupy the distant Oort cloud, a vast and poorly observed reservoir of icy bodies, may orbit the Sun at distances far greater than the heliopause. In that gravitational sense, a spacecraft can enter interstellar space while still moving through a region where the Sun remains the dominant gravitational anchor for remote material. This distinction matters because the solar system has several edges depending on what is being measured. The planetary edge lies near the outer planets. The main belt of trans-Neptunian objects extends farther. The solar wind boundary lies much farther still. The gravitational domain associated with distant comet reservoirs may extend farther again. There is no single fence that a spacecraft crosses and leaves everything solar behind at once. The transition is gradual, layered, and defined differently by different physical processes. For an interstellar mission, the heliopause is especially significant because it marks the point where the surrounding environment changes from solar to interstellar in a direct plasma sense. Yet even reaching that boundary with present spacecraft technology takes an appreciable portion of a human lifetime. This exposes one of the central scale problems before the true crossing has begun. Spacecraft built for planetary exploration already require long missions to reach the outer planets. A probe sent to Jupiter may spend years in transit. A probe sent to the far outer solar system may need close to a decade or more. Beyond the planets, propulsion is usually no longer producing continuous dramatic acceleration. The craft coasts, carrying the velocity earned during launch and any gravitational assists. Distances accumulate slowly, signals weaken, power becomes harder to supply from sunlight. The mission begins to depend on systems that must function for decades with little possibility of intervention. Every one of those difficulties appears before Alpha Centauri itself becomes a meaningful part of the immediate environment. The contrast between planetary and interstellar travel is therefore not merely a question of adding more distance to an ordinary mission. It changes the character of the mission. Within the planetary system, gravity assists can be arranged around massive worlds. Solar power may remain practical over significant portions of the route. Communication delays range from minutes to hours rather than years. Rescue is still unrealistic in most cases, but the Sun remains the central reference point and the mission takes place inside a well-mapped family of worlds. Once the heliopause is crossed, those conditions begin to fall away. There are no giant planets waiting ahead to redirect the trajectory. There are no convenient refueling points, no natural sequence of destinations, and no nearby source of strong sunlight. A spacecraft heading for Alpha Centauri is no longer traveling through a chain of places. It is traveling through distance itself. The local interstellar medium is not perfectly empty, but it is sparse enough that there may be no large object anywhere near the flight path for thousands of years at the speeds of current spacecraft. The Sun gradually contracts behind into another bright star. The destination remains unresolved ahead. Between them lies an environment that offers very little assistance and very little forgiveness. This is why the experience of Voyager 1 is both encouraging and sobering. It proves that machines can remain functional across decades, cross the heliopause, and return measurements from beyond the solar wind boundary. At the same time, it demonstrates how slowly even the fastest successful outward journeys unfold. More than 30 years were required simply to reach a region that, on the scale of the Alpha Centauri voyage, still lies close to home. A spacecraft bound for another star must pass all of these familiar and unfamiliar thresholds first: the orbit of the outer planets, the Kuiper belt, the thinning solar wind, the complicated outer heliosphere, and finally the heliopause. Only then does the solar system begin to fall away in a meaningful environmental sense. The dramatic part is not that these boundaries are difficult to cross individually. A sufficiently durable spacecraft moving outward will eventually cross them. The problem is what their crossing reveals. By the time the Sun's protective bubble is behind, the spacecraft has already completed a journey that humanity considers historic. Yet the real interstellar distance has barely begun. Voyager 1 moves through space at roughly 17 kilometers per second relative to the Sun, a speed that would be extraordinary almost anywhere on Earth. At that pace, the spacecraft would cross the distance from London to New York in only a few minutes. It could circle the Earth in well under an hour. Yet pointed toward Alpha Centauri, the same speed becomes almost painfully small. A journey of a little more than 4 light years at roughly that velocity would take on the order of 74,000 years. The number is so large that it no longer describes a mission in any familiar engineering sense. It describes a span of human history. A spacecraft launched at the beginning of recorded civilization would still be nowhere close to arrival, even if one imagines a departure tens of thousands of years before the first cities, before agriculture had transformed human societies, before most of the cultural world now taken for granted existed at all. The craft could still be traveling today. This is the central contradiction of current interstellar travel. Human machines are already fast enough to escape planets, cross the solar system, and enter interstellar space, but they are nowhere near fast enough to make the nearest stellar system a practical destination on human timescales. The difficulty comes from the relationship between distance and velocity. The trip to another planet is large but finite in a way existing propulsion can manage. Mars can be reached in months. The giant planets can be reached in years. The outer solar system may require decades. The nearest star demands a multiplication so severe that the same technology changes category. A spacecraft that seems fast inside the solar system becomes almost stationary when measured against interstellar separation. 17 kilometers per second is only a tiny fraction of the speed of light. Light crosses the gap to Proxima Centauri in a little more than 4 years. A Voyager-like spacecraft would need tens of thousands of years because it covers only a small piece of that light speed distance in the same amount of time. Nothing mysterious is happening. The arithmetic is simple. What makes it difficult is that current propulsion methods are built around a very different scale of travel. Chemical rockets release energy through reactions between fuel and oxidizer. They can produce enormous thrust. which is why they are so useful for lifting spacecraft away from Earth and changing velocity quickly. But their exhaust speeds are limited by the chemistry that produces them. A rocket must carry the propellant it intends to throw backward, and the faster the spacecraft needs to become, the more propellant is required. That additional propellant adds mass, which then requires still more propellant to accelerate. The relationship becomes increasingly severe as the desired change in velocity rises. For travel between planets, careful trajectories and gravitational assists can make chemical propulsion extremely effective. For travel between stars, the required leap in speed is too large. The problem is not that chemical rockets are crude. They are among the most powerful and sophisticated machines ever built. The problem is that the energy available per unit of propellant is far too low for the velocities that interstellar travel demands. A conventional spacecraft can be launched quickly, but it cannot continue accelerating toward a meaningful fraction of the speed of light without carrying an impossible burden of fuel. This limitation is reflected in the trajectories of the fastest probes already leaving the solar system. They were not accelerated continuously all the way outward. They received most of their velocity during launch and planetary encounters, then spent the long remainder of their journeys coasting. Voyager 1 gained a major part of its outward speed through its encounters with Jupiter and Saturn. Once beyond the planets, there was no sequence of engines steadily driving it faster toward the stars. It simply continued with the momentum already acquired, slowed only gradually by the sun's gravity as it moved farther away. This is entirely reasonable for a mission designed to study planets and the outer heliosphere. For Alpha Centauri, it exposes a fatal mismatch. Coasting at present-day interstellar probe speeds means accepting travel times longer than the duration of complex human civilization so far. The consequences extend far beyond patience. A mission lasting 74,000 years would have to survive conditions no engineered object has ever approached. Electronics, power systems, structural materials, and stored information would need to remain functional across geological timescales by human standards. The civilization that launched the spacecraft could change beyond recognition or disappear entirely. Languages would evolve, political systems, technologies, and even the biological future of humanity could shift. Any institution created to receive the spacecraft's data would have to maintain continuity longer than almost any cultural tradition known today. The spacecraft would not simply be crossing space, it would be crossing deep time. For an uncrewed probe, that alone is enough to make the mission almost meaningless under present assumptions. For a crewed mission, the timescale becomes even more extreme. No individual human lifetime could bridge it. A vessel would need to become a self-contained population, perhaps supporting many thousands of generations before arrival. Every problem of life support, reproduction, governance, genetic health, repair, and social continuity would have to be solved not for decades, but for a period comparable to the full spread of modern humans across large parts of the planet. At that point, the spacecraft would cease to resemble a vehicle and begin to resemble a moving world. Even this description may understate the difficulty, because the mission would need to function with no possibility of outside repair once it was far from the sun. The nearer star would remain ahead for almost all of its history. This helps explain why the phrase interstellar travel can be misleading when attached to current spacecraft. Voyager 1 is physically traveling through interstellar space, but it is not traveling to another star in any practical sense. Its current path will carry it through the galaxy, and over immense stretches of time it may pass relatively near other stars, but its mission was never designed as a direct stellar crossing. The same is true of other probes escaping the solar system. They demonstrate that leaving the sun's immediate plasma environment is possible. They do not demonstrate that stellar destinations are reachable on useful timescales. The distinction matters because distance alone does not define a journey. Duration determines whether a journey remains connected to the civilization that begins it. A voyage lasting several decades can still belong to one generation. A voyage lasting centuries can perhaps remain connected through institutions and descendants. A voyage lasting tens of thousands of years moves into another category, where even the meaning of arrival becomes uncertain. The spacecraft may reach its target, but the society that wanted the answer may no longer exist in anything like its original form. Alpha Centauri therefore forces propulsion into the center of the problem. The solar system can be crossed slowly because its useful destinations are separated by light hours rather than light years. The nearest stellar system cannot. If a mission is meant to return knowledge within a humanly meaningful span, its velocity must increase, not by a modest percentage but by orders of magnitude. That requirement is what pushes interstellar engineering away from conventional rockets and toward more speculative concepts. The critical question becomes not whether a spacecraft can leave the Sun, because that has already been done, but whether it can acquire and survive a speed that changes 74,000 years into something closer to a lifetime. Until that change is achieved, Alpha Centauri remains reachable only in the most literal sense. A machine can be aimed outward, and given enough time, it can cross the distance. But a journey that lasts longer than civilizations have existed is not merely slow transportation. It is a reminder that current technology belongs to the planetary scale, while the stars demand an entirely different relationship with speed. A spacecraft moving at 1% of the speed of light would be transformed by human standards. It would cross nearly 3,000 kilometers every second, fast enough to circle Earth in little more than 10 seconds. Yet even that velocity would still leave Alpha Centauri more than 4 centuries away. At 10% of the speed of light, the crossing falls to a little more than 40 years if the spacecraft simply coasts at that speed, ignoring the time required to accelerate and slow down. Only when a vehicle begins to reach a substantial fraction of a light speed does the nearest stellar system move from the timescale of civilizations toward the timescale of a human life. That is, the threshold interstellar engineering keeps returning to. The problem is no longer how to make a rocket somewhat faster than Voyager 1. The problem is how to increase velocity by thousands of kilometers per second while carrying a spacecraft that can survive the process. Light itself sets the scale. In a vacuum, nothing with mass can be accelerated to the speed of light, and the closer an object comes to that limit, the more energy is required to increase its speed further. But an interstellar probe does not need to reach the limit for the journey to change radically. At 1/10 of light speed, Alpha Centauri becomes a multi-decade destination. At 1/5, the coast time falls to a little more than 20 years. Those are still long missions, but they belong to a recognizable span of technological and institutional memory. A probe could be designed by one generation and perhaps return its first distant measurements, while some of the people involved in its creation were still alive. Reaching those velocities, however, requires propulsion methods far beyond the ordinary chemical engines that launch spacecraft from Earth. One possible direction is fusion propulsion. Fusion is the process that powers stars, combining light atomic nuclei and releasing energy from the difference in mass between the initial particles and the products. In principle, a spacecraft could use repeated fusion reactions to heat and expel propellant at far greater exhaust velocities than chemical combustion allows. The attraction is not mysterious. Faster exhaust means a rocket can achieve a much larger change in velocity without requiring an overwhelming mass of propellant. Several fusion propulsion concepts have been studied in different forms, often using magnetic fields to contain or direct extremely hot plasma. None has yet become an operational interstellar engine. Controlled fusion on Earth is itself a demanding technological problem. and a propulsion system would have to make the process compact, reliable, lightweight, and capable of surviving continuous operation in space. Even so, fusion remains important because it shows the kind of energy density required once the target velocity moves beyond the planetary scale. Antimatter occupies an even more extreme position. When matter and antimatter meet, their mass can be converted into other forms of energy with exceptional efficiency. In theory, this makes antimatter one of the most energy-dense propulsion possibilities known to physics. A small amount could release far more energy than an equal mass of chemical fuel. The difficulty is that antimatter is not available as an ordinary fuel resource. It has to be produced, collected, and stored, and present production methods create only tiny quantities at enormous energetic and financial cost. Storage is also severe because antimatter cannot be allowed to touch ordinary matter without annihilating. Concepts involving antimatter therefore remain far from practical starship engineering. Although research has examined whether very small quantities might trigger or assist other nuclear reactions rather than serve as the sole energy source. Both fusion and antimatter share a basic architecture familiar from rockets. Energy is carried with the vehicle, and momentum is gained by throwing something backward. A different strategy is to leave much of the energy source behind. Beamed propulsion does this by directing energy toward a spacecraft from a distant installation. A light sail can use the pressure of photons, particles of light, to produce thrust without carrying conventional propellant. The force from each photon is tiny, but a sufficiently intense beam acting on an extremely lightweight reflective sail can accelerate the craft continuously for a period of time. The most widely discussed modern example is Breakthrough Starshot, a research initiative built around the idea of sending gram-scale probes toward Alpha Centauri. Instead of accelerating a large spacecraft with an engine and fuel tanks, the concept uses a powerful ground-based light source to push very small spacecraft attached to ultralight sails. The target is roughly 1/5 of the speed of light, fast enough for a flyby of Alpha Centauri a little more than 20 years after launch. The concept is striking not because such a mission has already become feasible, but because it attacks the mass problem directly. A gram-scale probe needs vastly less kinetic energy than a crude vehicle weighing thousands of tons. A sail also avoids carrying the energy source that accelerates it during the initial boost. In principle, a large laser array near Earth could deliver energy to the sail while the spacecraft remains relatively close, pushing it to extraordinary speed before the beam becomes too spread out to remain effective. After that acceleration phase, the probe would coast through interstellar space. This shifts the engineering burden rather than removing it. The laser system would have to deliver immense power with extraordinary control. The beam would need to remain accurately directed onto a sail accelerating rapidly away from Earth. The sail would have to be extremely light, highly reflective, and resistant to heating. The spacecraft attached to it would need cameras, sensors, computation, communication equipment, and power in a package measured in grams rather than tons. It would then have to survive more than 2 decades of flight at a velocity where encounters with gas and dust become serious hazards. The design also assumes a fast flyby rather than an easy stop at the destination, because carrying the machinery required for major deceleration would undermine the very low mass that makes the concept attractive. This difference between a tiny probe and a human spacecraft is fundamental. The faster a mission needs to travel, the more brutally mass enters the equation. A probe can discard almost everything except instruments, communication systems, and the structure required to keep them alive. A human mission cannot. It must carry living space, environmental control, food production or storage, water recycling, radiation protection, medical capability, redundancy, and enough structure to protect a crew for decades. Every added kilogram must be accelerated. If the vehicle carries its own fuel, some of the mass is fuel needed to accelerate other fuel that will be burned later. If it also intends to stop, the problem becomes more severe again. This is why a speed that sounds like a simple percentage becomes an architectural divide. 1% of light speed is already far beyond the velocity of conventional spacecraft, yet it still produces a journey lasting centuries. 10% brings the trip into the range of decades, but demands propulsion and energy systems that have never been built at the required scale. 20% makes a fast robotic mission conceptually attractive, but only by reducing the spacecraft to something extraordinarily small and accepting a brief encounter at the far end. The speed of light is therefore not merely a distant physical limit. It acts as a ruler that exposes how narrow the useful band of interstellar velocity really is. Too slow, and the mission disappears into deep time. Fast enough to matter, and the engineering problems become extreme almost immediately. Alpha Centauri does not require a spacecraft to challenge the absolute limit set by relativity. It requires something more subtle, and perhaps more difficult to machine, capable of reaching a meaningful fraction of that limit while remaining light enough to accelerate, durable enough to survive, and useful enough to justify the journey. Once that requirement is accepted, speed stops being only a question of propulsion. It becomes a question of how much energy civilization is willing to concentrate into a moving object, and that cost grows rapidly as the desired velocity rises. At interstellar speeds, mass becomes a form of resistance long before the spacecraft encounters anything outside itself. Every kilogram carried toward Alpha Centauri has to be accelerated, and the faster the vehicle is meant to travel, the more energy must be invested in that motion. At low speeds, the relationship is already demanding doubling velocity requires far more than doubling the kinetic energy. At a significant fraction of the speed of light, the problem becomes more severe still, because relativistic effects begin to matter, and the energy needed for each additional increase in speed rises rapidly. This is why discussions of interstellar propulsion often become discussions of mass almost immediately. A small probe and a crewed spacecraft may share the same destination, but energetically they belong to completely different categories. A probe weighing only a few grams can be imagined as a thin sail, a sensor package, a computer, and a communication system. A crewed ship must carry structure, shielding, power systems, life support, food or food production, water, atmosphere, thermal control, medical capability, repair equipment, and enough redundancy to survive failures across decades. The difference is not merely one of convenience. Every added component increases the energy required to reach the target velocity, and any fuel carried for later use must itself be accelerated along with the rest of the vehicle. This creates a severe feedback problem. More mass requires more energy. More onboard energy often requires more fuel or larger machinery. That additional fuel and machinery add more mass, which then demands still more energy. Conventional rockets already suffer from this problem because they must carry the propellant they intend to expel. Interstellar rockets face the same logic on a far more punishing scale. The desired velocity is so high that simply enlarging a familiar spacecraft does not produce a practical solution. It creates a vehicle increasingly dominated by the systems required to move its own mass. The difficulty becomes clearer when acceleration is separated from travel time. A spacecraft does not begin its journey already moving at 1/10 or 1/5 of the speed of light. Something has to supply the energy that brings it there. If the acceleration is intense and brief, the propulsion system must deliver an extraordinary amount of power in a short period. If the acceleration is gentle and prolonged, the engine must continue operating reliably for much longer. carrying or receiving energy throughout that period. Either approach moves far beyond ordinary spacecraft design. A beamed sail avoids carrying much of the acceleration energy because the power source remains near the solar system. But that advantage works best for a very light spacecraft. A heavy sail large enough to carry substantial equipment becomes hard to accelerate. A fusion vehicle may carry an energy source with much greater potential than chemical fuel, but it must also carry the machinery that controls the reactions, converts the released energy into directed thrust, and rejects waste heat. Antimatter concepts offer exceptional energy density in principle, but they intensify the challenges of production, handling, containment, and conversion into useful propulsion. In every case, the central question is not simply whether enough energy exists somewhere in nature. The question is whether that energy can be generated, stored, transferred, and controlled by a real spacecraft without making the spacecraft too massive to accelerate in the first place. This distinction is what makes gram-scale concepts so important. Reducing mass does not make the physics easy, but it changes the scale of the engineering problem dramatically. A probe light enough to be pushed by a powerful laser can, at least in principle, reach velocities that would be completely unrealistic for a vehicle carrying a large internal propulsion system. The spacecraft gives up almost everything in exchange for speed. There may be no large telescope, no heavy shielding, no abundant power reserve, no elaborate propulsion system waiting for arrival, and no comfortable margin for redundancy. The design becomes a compressed package built around only the functions that matter most. For a robotic flyby, this trade can make sense. The probe needs to survive the crossing, gather observations during a brief encounter, and send information home. A human mission cannot make the same trade without losing the conditions that make human survival possible. A person cannot be reduced to a sensor chip. Human beings require a surrounding environment, and the systems that maintain that environment have mass. Radiation shielding has mass, pressure vessels have mass, water has mass, spare parts have mass. Even if food is produced during the voyage rather than stored for the entire journey, the equipment needed to grow and recycle biological resources has mass. If artificial gravity is created through rotation, the structural system must withstand that rotation. If large protective layers are added against radiation and dust, the vehicle becomes heavier again. At interstellar velocity, each of these necessities becomes part of the propulsion problem. The most difficult consequence appears at the far end of the journey. Accelerating a spacecraft is only half of a true arrival mission. A vehicle moving at a large fraction of a light speed carries an enormous amount of kinetic energy, and that energy does not disappear when Alpha Centauri comes into view. If the spacecraft continues on its original path, it will pass through the system and leave again. To remain near one of the stars, enter a useful trajectory, or settle into orbit around a planet, much of that velocity must be removed. The same basic energetic challenge that made acceleration difficult now returns in reverse. A spacecraft that carries fuel for braking must accelerate that braking fuel during the entire outward journey. The penalty is immediate. Mass intended only for the destination increases the energy required at departure. Additional fuel may then be needed to accelerate that fuel, and the design begins to compound against itself. This is one reason flyby missions are so much easier to imagine than missions that stop. A fast probe can use almost all of its energy budget to gain velocity, cross the interstellar distance, and accept that the encounter at Alpha Centauri will be brief. A stopping mission must reserve some method of shedding speed. That could involve onboard propulsion, interaction with magnetic fields or stellar wind, some form of sail used against radiation from the destination star, or another braking concept. But every method introduces constraints, uncertainty. and often additional mass. The energy problem therefore shapes not only how fast a spacecraft can travel, but what kind of mission it can perform once it arrives. A tiny probe might reach Alpha Centauri within a few decades, yet collect only a short burst of data during a high-speed passage. A heavier scientific spacecraft might carry better instruments and stronger communications, but accelerating it to the same speed would demand far more energy. A crewed vessel would add another enormous layer of mass and would almost certainly require deliberate deceleration, making the energetic burden greater again. The destination may be identical on a map, but the physical cost of reaching it changes with every kilogram and every mission requirement. This is the point where the phrase interstellar speed loses its simplicity. Speed is not a property that can be added to a spacecraft without consequence. It is stored energy. The faster the vehicle moves, the more destructive that energy can become in a collision, the harder the spacecraft becomes to redirect, and the more difficult it is to stop. Propulsion is therefore tied directly to shielding, navigation, structure, and mission architecture. A change intended to solve one problem can enlarge several others. More shielding improves protection but raises mass. More fuel permits larger velocity changes but raises mass. More redundancy improves reliability but raises mass. Larger radiators may be needed to remove waste heat from powerful propulsion systems, and they also raise mass and structural complexity. The interstellar vehicle becomes a balance in which almost every safety margin has an energetic price. This is why the smallest proposed probes occupy such a different technological space from imagined human starships. The underlying distance is the same, and the desired fraction of light speed may be similar, but energy scales with what has to be moved. A civilization might eventually learn to generate tremendous amounts of power, yet the engineering question would remain how much of that power can be turned into controlled motion without destroying the vehicle, wasting most of the energy, or requiring so much hardware that the mass becomes self-defeating. Alpha Centauri does not merely demand a faster engine. It demands an architecture in which mass, energy, acceleration, braking, heat, and survival are designed as one connected problem. Only after that balance is solved does the idea of crossing 4 light-years begin to resemble a journey rather than a calculation. And even then, the energy stored in that speed creates a new danger, because once a spacecraft is moving fast enough to make the stars reachable, even the smallest pieces of matter ahead can strike with consequences far beyond their size. At a significant fraction of the speed of light, interstellar space stops behaving like emptiness. The gas between the stars remains extraordinarily thin by terrestrial standards, and the dust mixed through it is sparse enough that a slow-moving spacecraft might pass through without noticing most individual encounters. Speed changes the meaning of that environment. A hydrogen atom striking a vehicle at ordinary spacecraft velocity carries very little energy. The same atom meeting a probe moving at 1/10 or 1/5 of the speed of light arrives with vastly more kinetic energy. A grain of dust that would seem harmless on a laboratory table can become a compact impactor capable of releasing destructive energy into a tiny area. This is one of the most severe consequences of making Alpha Centauri reachable within decades. The faster the spacecraft becomes, the more dangerous even the thinnest material ahead becomes, and the vehicle has no choice but to cross several light-years of it. The local interstellar medium is not a perfect vacuum. It contains mostly hydrogen and helium in neutral and ionized forms, along with traces of heavier elements and a much smaller population of solid grains. The average density is extremely low, but the path to Alpha Centauri is so long that the spacecraft encounters an enormous column of space. Individual atoms are not the same threat as a large dust particle, yet at relativistic velocity they can still erode surfaces, heat exposed materials, implant particles into shielding and gradually damage delicate structures. A stream of atoms striking the nose of a spacecraft is less like a gentle breeze than a continuous rain of high-energy particles. The effect may be distributed and subtle compared with a single catastrophic collision, but over decades the accumulation matters. Dust creates the more dramatic problem because mass is concentrated into individual grains. Interstellar grains can range from tiny particles much smaller than the width of a human hair to larger fragments that are rarer but more dangerous. Their exact abundance along any future flight path would need careful measurement, because risk depends not only on average density, but on the chance of encountering an unusually large particle. At low velocity, such a grain might produce a small pit in a surface. At a substantial fraction of light speed, the collision can vaporize the grain and part of the spacecraft material almost instantly, creating a burst of plasma, radiation, and secondary fragments. The damage is not limited to the point of contact. Energy spreads into the surrounding structure, and material ejected from the impact can become a new source of internal destruction. A spacecraft moving this quickly therefore cannot treat its forward surface as ordinary skin. The leading edge becomes one of the central systems of the mission. It must absorb, deflect, vaporize, or otherwise survive whatever lies ahead without becoming so massive that the vehicle can no longer be accelerated efficiently. That trade is severe. More shielding generally means more protection, but every additional layer adds mass, and mass has already become one of the dominant costs of interstellar flight. A thick block of material placed at the front might protect equipment behind it, yet accelerating that block to relativistic speed demands additional energy. If the spacecraft is a gram-scale probe pushed by a laser sail, the problem is even sharper. The entire mission concept depends on extreme lightness. Heavy armor could erase the advantage that makes the probe fast enough to reach Alpha Centauri within decades. Protection therefore has to be clever rather than simply massive. One possible strategy is to use sacrificial shielding. Instead of expecting the outermost layer to remain pristine, the design allows it to absorb impacts and gradually erode. Materials with suitable thermal and mechanical properties could be placed ahead of sensitive electronics, giving the spacecraft a protective thickness that is consumed over the voyage. Another approach is to separate shielding from the main structure, placing thin layers or clouds of material in front so that incoming grains strike something before reaching the vehicle itself. The first collision could fragment or vaporize the particle, spreading its energy over a wider area when the debris reaches the next layer. This resembles the logic of shields already used against micrometeoroids on spacecraft, but the velocity regime of an interstellar probe is far more extreme. Techniques effective at orbital speeds cannot simply be scaled upward without new physics and materials questions. Magnetic or electric fields offer another possibility for charged particles. A sufficiently strong field can redirect ions and some plasma before they hit the spacecraft, reducing direct exposure to part of the interstellar gas. Neutral atoms and solid grains are harder. They do not respond in the same way unless they can first be ionized or otherwise altered. Some concepts therefore imagine using lasers, particle beams, or electromagnetic systems to detect or interact with material ahead of the craft. The difficulty is range and reaction time. At 1/5 of light speed, the spacecraft crosses an enormous distance every second. A hazard detected far ahead by ordinary standards may still leave almost no time for mechanical avoidance. The vehicle cannot simply turn sharply around each grain. Its momentum is too large, its path too fast, and the particles too numerous or too difficult to observe individually. For the smallest dust grains, the mission must assume collision rather than evasion. This changes the role of navigation. The goal is not to find a perfectly empty corridor through interstellar space, because no such guaranteed corridor is likely to exist. The goal is to choose a path whose gas and dust environment is understood well enough that shielding can be designed around realistic probabilities. Astronomical observations can estimate the properties of the local interstellar medium, but a future high-speed mission would benefit from much more detailed knowledge of the exact line of sight. Even then, the smallest dangerous particles may be impossible to map individually before launch. The spacecraft must therefore survive uncertainty as well as known conditions. The problem becomes especially difficult because impacts can affect more than the main body. A light sail may be large and extremely thin. A communication antenna may require delicate geometry. Sensors may need exposed apertures. Any component facing forward or extending beyond the protective shadow of the shield could become vulnerable. Designing the vehicle around a narrow protected cone may help, with the strongest shielding at the nose and critical systems placed behind it, but the spacecraft still needs to observe its destination, communicate with Earth, manage heat, and perhaps reorient itself during the mission. Each function can expose surfaces that would otherwise remain protected. A high-speed probe is therefore shaped by the direction of travel in a way that slower spacecraft are not. Forward and backward are physically different environments. The front faces a persistent bombardment. The rear may carry communication hardware aimed toward the receding solar system. The sides remain less exposed but cannot be treated as invulnerable if the craft changes attitude. For a crewed ship, the same problem grows with size. A larger cross-sectional area intercepts more material. More shielding is required, but that shielding adds enormous mass. A human vessel cannot simply accept gradual penetration through critical living spaces. The hull would need multiple defensive layers, extensive redundancy, and perhaps large stores of shielding material positioned ahead of the inhabited sections. Water or other mission consumables might serve partly as radiation and impact shielding, but their mass still has to be accelerated and later decelerated. The geometry could resemble a long vehicle with the most vulnerable systems buried deep behind a protective forward mass. Even this does not eliminate the possibility of a rare larger grain producing damage beyond what the design can absorb. At interstellar speed, small probabilities become important because the journey is so long and the consequences of failure are so high. There is no repair station between the Sun and Alpha Centauri. A puncture, damaged radiator, severed cable, or destroyed sensor that might be recoverable near Earth could become a mission-ending event if the spacecraft lacks redundant systems and autonomous repair. The unsettling feature of the dust problem is that it emerges only after propulsion begins to succeed. At Voyager-like speeds, the journey takes too long to be useful, but the interstellar medium is comparatively gentle. Increase speed enough to reduce the crossing to decades, and the same medium becomes hostile. The solution to the time problem creates a collision problem. More velocity means more impact energy. More shielding means more mass. More mass means more energy required for acceleration and braking. The problems lock together, making it impossible to optimize one without affecting the others. This is why an interstellar spacecraft cannot be designed as an ordinary probe with a faster engine attached. Its entire structure has to be built around the fact that motion itself has changed the environment. The empty distance between stars becomes an active physical medium, thin but relentless, and the spacecraft carries the energy that makes every encounter dangerous. Alpha Centauri may be separated from the Sun by almost nothing compared with the size of the galaxy. Yet a vehicle crossing that small galactic gap at useful speed would spend decades driving through a stream of particles powerful enough to reshape its surface one collision at a time. And while shielding can be placed in front of the craft to meet that threat, another form of bombardment arrives from every direction. One that cannot be stopped merely by putting a thicker wall at the nose. Beyond the heliosphere, the protective influence of the Sun becomes weaker, but the larger radiation environment of the galaxy does not disappear. A spacecraft traveling toward Alpha Centauri would move for years through a region filled with high-energy particles arriving from many directions, some produced by distant stellar explosions and other violent astrophysical processes. On Earth, much of this radiation is softened before it reaches living tissue. The atmosphere provides a deep layer of material that absorbs and scatters incoming particles, while the planet's magnetic field deflects many charged particles away from the surface. A spacecraft between the stars has neither protection by default. Its hull may stop low-energy particles and ordinary debris, but the most energetic cosmic rays can penetrate deeply into materials, create secondary showers of particles inside the structure, damage electronics, and pass through living tissue. The danger is not that interstellar space contains one invisible wall of radiation waiting beyond the solar system. The danger is exposure accumulated slowly across an entire journey. Galactic cosmic rays are mostly atomic nuclei moving at very high energies. Hydrogen nuclei are common, but heavier nuclei are especially important because they can deposit large amounts of energy along narrow tracks as they pass through matter. A single particle may cross a spacecraft in an instant, yet the mission lasts for decades. Over time, countless interactions add together. In electronics, energetic particles can disturb memory, corrupt data, alter individual bits, degrade sensors, and damage semiconductor components. Some events are temporary and can be corrected by redundant systems. Others can gradually weaken hardware or cause permanent failure. Spacecraft operating near Earth already contend with radiation, and missions beyond Earth's magnetic protection must be designed with hardened components and fault-tolerant software. An interstellar mission extends that requirement across a duration and distance for which no repair crew or replacement launch can provide practical help. Radiation damage therefore becomes part of the reliability budget from the moment the spacecraft leaves the protection of Earth. For human passengers, the same environment becomes more complicated because living tissue cannot simply be rebooted. High-energy particles can ionize molecules as they pass through cells, breaking chemical bonds and damaging genetic material. Biological systems can repair a great deal of damage, but repair is not perfect, and repeated exposure raises the probability that errors accumulate. The long-term concerns include increased cancer risk, injury to the central nervous system, cardiovascular effects, cataracts, and other forms of tissue damage whose severity depends on dose, particle type, energy, and individual biology. Space agencies study these risks for missions lasting months or years, including potential expeditions beyond low Earth orbit. A voyage to Alpha Centauri compresses no new law of biology into the problem. It simply extends the exposure window until small rates become strategically important. A crew traveling for several decades could not rely on the same assumptions as astronauts protected by short mission duration and the possibility of returning to Earth. The vehicle itself would have to become a permanent radiation shelter. Shielding sounds simple until the particles involved are considered. Dense material can block or reduce many forms of radiation, but extremely energetic charged particles do not always behave conveniently when they strike a heavy shield. A collision with a nucleus in the shielding can fragment the incoming particle and the target atom, producing secondary particles that continue deeper into the spacecraft. Adding more material generally helps after sufficient thickness, but the choice of material matters. Substances rich in hydrogen are often useful because hydrogen nuclei are light and can reduce the production of some damaging secondary radiation compared with very heavy shielding materials. Water, polyethylene-like materials, fuels, food stores, and other hydrogen-rich substances can therefore perform more than one role in a crewed spacecraft. Water needed for life support might be stored around inhabited areas, Supplies might be arranged so that mass already required for survival also contributes to shielding. This kind of dual use is attractive because interstellar vehicles cannot afford to carry large masses that serve only one purpose. Even so, meaningful shielding for a crew would still add substantial weight. That weight feeds directly back into propulsion. A thin robotic probe may tolerate radiation by using hardened electronics, redundancy, error correction, and perhaps a modest protective layer around critical components. If one processor fails, another may take over. If memory is corrupted, duplicated records may allow recovery. The probe can also be designed without the biological limits that constrain a human crew. A crewed ship has a much larger protected volume and must keep radiation exposure within survivable limits across decades. Thickening the walls increases mass. Increasing mass raises the energy needed for acceleration. Additional propulsion hardware may then add still more mass. The same chain that appeared with impact shielding appears again, but radiation is harder to localize because it does not arrive only from the direction of travel. Dust and gas are most dangerous at the forward edge because the spacecraft is moving into them. Galactic cosmic rays can arrive from a broad range of directions. A protective nose alone cannot solve the problem. The inhabited volume may need shielding around much of its structure, or at least a heavily protected central refuge where the crew can spend long periods. Solar activity does not become irrelevant immediately after departure either. During the early part of the mission, energetic particles from solar eruptions can create intense short-term radiation events. These are different from the persistent background of galactic cosmic rays. Solar particle events can increase rapidly and may deliver a dangerous dose over a much shorter interval. A crewed spacecraft would likely need a storm shelter surrounded by water, supplies, or dedicated shielding for periods of elevated activity. Farther from the Sun, those events weaken as the spacecraft leaves the inner heliosphere. But the broader galactic radiation environment remains. In fact, the heliosphere itself provides some modulation of lower energy galactic cosmic rays. So crossing into interstellar space does not create a cleaner radiation environment. It removes one layer of solar influence while exposing the spacecraft more directly to the local interstellar particle population. The uncertainty matters almost as much as the average exposure. Radiation risk across a multi-decade mission depends on the shielding geometry, the spacecraft's trajectory, solar conditions during departure, the local interstellar environment, and the biological effects of particle types that are difficult to reproduce fully on Earth. Experiments can study components of the problem, but no laboratory can place a complete human habitat in the true interstellar radiation field for decades before the mission begins. Engineers would therefore have to design around models, shorter observations, particle accelerator experiments, and data from spacecraft traveling beyond Earth. Safety margins would need to account for a future environment that can be characterized but never perfectly predicted. The spacecraft would also need to monitor its own exposure continuously, identifying damaged systems and adjusting operations as the accumulated dose rises. For electronics, this may encourage architectures built around redundancy rather than permanence. Computers could be duplicated, isolated, checked against one another, and designed to recover from corrupted states. Critical information could be stored in multiple physical locations. Sensors might be protected behind shielding except when needed. Components could be powered down when inactive to reduce some forms of vulnerability. A long mission may also require spare electronics or reconfigurable hardware able to replace functions lost gradually to radiation. These approaches add complexity, but they acknowledge a central fact: the spacecraft cannot assume that every component launched from the solar system will remain unchanged until arrival. For a human crew, adaptation is more limited. medicine may reduce some consequences. Monitoring may detect damage earlier, and future biotechnology could improve protection or repair. But no known method makes prolonged high-energy radiation irrelevant. The simplest protection remains placing matter between the crew and the particles, and matter is exactly what an interstellar spacecraft struggles most to carry. This creates another quiet conflict at the heart of the journey. Propulsion rewards lightness, survival rewards shielding. The faster mission already demands extreme energy, and the safest vehicle tends to become heavier as protection improves. Radiation therefore turns the space between stars into a long-duration environment rather than a neutral gap. The threat is rarely dramatic from moment to moment. There may be no visible flash and no single instant when the voyage becomes unsafe. Instead, particles cross the hull, electronics record faults, materials slowly accumulate damage, and living cells absorb a dose that grows with time. A robotic probe can be made small, hardened, and expendable enough to accept part of that risk. A human spacecraft must preserve an entire habitable environment while the exposure continues from year to year. Crossing 4 light-years means protecting not only against what the vehicle might hit, but against what can pass through it. And once that protection is added, another requirement emerges: every shield, computer, pump, recycler, and power source must continue working for the entire voyage with no workshop, supply chain, or rescue mission anywhere ahead. An interstellar spacecraft cannot depend on rescue. Once it is far beyond the outer solar system, every system required for survival must either continue working or be repaired using what is already on board. That changes the meaning of reliability. On an ordinary spacecraft mission, engineers still design for redundancy, but the vehicle remains connected to a broader civilization. Ground teams can diagnose problems. Replacement missions may be possible. Updated software can be transmitted. Scientific goals can be reduced if equipment fails. A journey to Alpha Centauri removes most of those options. The spacecraft becomes a sealed technical ecosystem that must preserve its own function through years or decades of operation. And for a crewed mission, failure is not merely a loss of data. It can mean the loss of breathable air, usable water, temperature control, food production, or medical capability. Power sits at the center of the problem, near Earth. Sunlight is abundant enough for solar panels to support a wide range of spacecraft. Farther from the Sun, the available solar energy falls rapidly with distance. By the time a vehicle is deep into interstellar space, the Sun is only one star among many in terms of appearance, and solar power from it becomes far too weak to support a large mission. An interstellar craft therefore needs an energy source that travels with it, or a system capable of receiving power across extreme distance. And the latter becomes progressively difficult once the spacecraft leaves the region where a concentrated beam can be delivered effectively. Small probes may rely on long-lived nuclear sources or other compact power systems, but a human ship would require much more: pumps, computers, environmental controls, lighting, thermal management, navigation, communications, medical equipment, workshops, and possibly food production systems all need continuous energy. If propulsion remains active for part of the journey, the demand rises dramatically again. A power system must therefore do more than produce enough energy on launch day. It must remain stable after years of radiation exposure. Thermal cycling, vibration, material aging, and the slow degradation of components that cannot be replaced from Earth. Electrical reliability is only one layer. Every moving part becomes a long-term liability. Pumps wear, bearings degrade, valves stick, seals leak, filters clog, lubricants change under radiation and temperature. Electronic components fail unpredictably. Even materials that appear static can suffer fatigue, embrittlement, corrosion, or microscopic damage accumulated across time. The problem is not that engineers do not know how to build durable machines. The problem is that a starship would need durability across nearly every subsystem at once, and many of those systems would depend on one another. A failed cooling loop can overheat electronics. A power fault can stop air circulation. A damaged sensor can cause a control system to make the wrong correction. A software error can turn a mechanical problem into a mission-wide failure. Reliability, therefore, has to be architectural rather than local. Critical functions would need multiple pathways, isolation between subsystems, fault detection, and the ability to operate in degraded modes without collapsing the entire vehicle. A robotic probe can address some of this with redundancy and simplicity. Fewer moving parts, smaller computers, limited scientific objectives, and tightly controlled power use all improve the chance of survival. If one instrument fails, another may still operate. If the craft loses some capacity, the mission can continue at reduced performance. A human vessel does not have that freedom. Life support cannot be treated as optional payload. Oxygen must be maintained continuously. Carbon dioxide must be removed. Water must be recovered, purified, and redistributed. Temperature and humidity must remain within tolerable ranges. Waste must be processed or stored safely. Food must either be carried in enormous quantities or produced in some renewable system. Each of those functions creates its own equipment, and each piece of equipment becomes something that can fail. A closed-loop life support system attempts to recycle resources instead of constantly consuming them. Water from respiration, hygiene, and waste can be cleaned and reused. Carbon dioxide can be removed from the air and perhaps incorporated into biological or chemical cycles that restore oxygen. Nutrients can be recovered rather than discarded. The more complete the recycling, the less mass must be launched as consumable supply. But greater closure usually means greater complexity. A nearly self-sustaining system requires sensors, pumps, filters, chemical processes, biological components, and control software working together for long periods. On Earth, ecosystems recycle matter through vast networks that have developed over immense spans of time. A spacecraft would need to reproduce only the parts required for survival, but it would have to do so inside a limited volume with little tolerance for instability. Food creates another challenge because storage alone becomes unattractive as mission duration grows. Preserved food can last for significant periods, but carrying decades of meals for a large crew would add major mass and would not solve nutritional degradation indefinitely. Growing at least part of the food aboard the spacecraft offers a possible alternative. Plants can convert carbon dioxide into oxygen while producing edible biomass, making them useful in more than one system. Yet agriculture in space introduces new dependencies. Crops need light, water, nutrients, controlled temperature, and protection from disease. A failed harvest in an isolated spacecraft is not a temporary economic loss. It can become a survival crisis. A robust ship would therefore need diversity, stored reserves, multiple growing areas, and the ability to recover from biological failure without outside assistance. Human health adds still another set of long-duration requirements. Extended exposure to microgravity alters bone, muscle, circulation, balance, and other physiological systems. Exercise can reduce some effects, but a voyage lasting decades may require more than continuous exercise equipment. Artificial gravity created through rotation is one possible solution, using centrifugal effects to produce a persistent downward force inside part of the spacecraft. The idea is physically straightforward. But building it into an interstellar vehicle adds structural mass and moving geometry. A rotating habitat must remain balanced. Bearings or joints, if used, must endure long service. The structure must withstand forces throughout the mission, and the spacecraft must still navigate and protect itself while part of it rotates. Once again, a solution to one survival problem makes the total machine more complicated. Maintenance becomes unavoidable. The idea of building every component so perfectly that nothing fails for several decades is unlikely to be enough. A more realistic interstellar vehicle would need to expect failures and treat repair as a normal part of operation. That means carrying tools, diagnostic systems, spare parts, raw materials, and perhaps manufacturing equipment capable of producing replacements. Additive manufacturing and automated machining could reduce the need to carry every possible component in advance. But manufacturing still requires feedstock, energy, precision, and designs. Some parts are easy to fabricate. Others depend on complex electronics, specialized materials, or manufacturing environments that are difficult to reproduce inside a spacecraft. A truly resilient ship might need layers of repair capability. From simple replacement of modular components to local fabrication and automated inspection of structures that humans cannot safely reach. For a robotic interstellar probe, autonomous self-repair would be even more important, because there may be no crew present to intervene physically. The spacecraft would have to detect faults, isolate damaged systems, reroute power, and perhaps reconfigure hardware without waiting for instructions from Earth. Artificial intelligence may assist with diagnosis and planning, but intelligence does not remove the need for physical redundancy. A computer can identify a broken pump, but the craft still needs another pump, a repair mechanism, or a different way to circulate the fluid. Software can compensate for some failures. It cannot replace missing matter. This distinction becomes more severe as communication delays increase, even before the spacecraft reaches Alpha Centauri. A request for guidance from Earth may take years to receive an answer once the full round-trip delay is considered. The crew or onboard systems must therefore possess enough knowledge to solve unfamiliar failures independently. The spacecraft is no longer simply a vehicle carrying passengers through space. It is a moving concentration of industrial capability, environmental control, medical support, computation, and stored knowledge. Its most valuable resource may not be any single machine, but the ability to recover when machines stop behaving as expected. That requirement changes the design philosophy of the entire mission. A conventional spacecraft can be optimized around a defined lifetime. An interstellar ship has to be optimized around graceful aging. Components will degrade, performance will drift, some systems will be lost. The goal is not perfect preservation, but continuous function despite damage, radiation, wear, contamination, and human error. Redundancy must be balanced against mass. Simplicity must be balanced against flexibility. Repair capability must be balanced against the complexity introduced by carrying a workshop. Life support must be efficient enough to conserve resources, but understandable enough to restore when something fails. Every choice remains tied to propulsion, because every spare part, every liter of water, every shield, and every machine must be accelerated to interstellar velocity. This is why survival across 4 light-years is not a passive problem. The spacecraft cannot simply remain intact and wait for Alpha Centauri to arrive. It must actively maintain itself every day of the crossing. Air must be circulated, water recycled, heat moved, power generated, faults detected, materials inspected, biological systems managed, and damaged components replaced. For decades, That work continues while the ship moves through a region where no external infrastructure exists. The success of the mission depends less on building a machine that never fails than on building one that can fail repeatedly without dying. And even if that problem is solved, the spacecraft still cannot simply point itself at the bright position of Alpha Centauri and coast toward it, because over the decades of travel, the destination itself continues to move. Alpha Centauri is not fixed in the sky. The apparent point of light seen from Earth is only a changing projection of a system that is moving through the galaxy, while the Sun moves as well. A spacecraft leaving the solar system cannot aim at the position where Alpha Centauri appears at launch and assume the stars will remain there for the duration of the journey. If the crossing lasts several decades, the target will have shifted by the time the vehicle arrives. The trajectory must therefore be calculated as an interception, not a simple straight line toward a static object. This is familiar in planetary navigation, where spacecraft are aimed toward the future positions of planets, rather than their current locations. But the interstellar version magnifies the consequences because the distances and travel times are so much larger. The basic motion can be separated into several layers. The Sun orbits the center of the Milky Way. Alpha Centauri also moves through the galaxy on its own path. Within the Alpha Centauri system, the stars move relative to one another. Alpha Centauri A and Alpha Centauri B orbit a common center of mass, while Proxima Centauri occupies a much wider orbit around the pair. None of these motions is fast compared with light, but over decades they become large enough that an interstellar spacecraft must account for them precisely. The destination is therefore a moving three-dimensional volume rather than a bright coordinate painted on the sky. Astronomers measure stellar motion using position, distance, radial velocity, and proper motion. Proper motion describes the apparent drift of a star across the sky, relative to more distant background objects. Radial velocity measures motion toward or away from the observer. Combined with distance, these observations allow the star's motion through space to be reconstructed. For Alpha Centauri, the measurements are good enough that future positions can be predicted with high confidence over mission timescales, but the spacecraft still has to use those predictions correctly. A probe traveling for 20, 40, or more years must leave with an aim point based on where its chosen target is expected to be when the probe reaches the system. That aim point will not correspond exactly to the star's visible location at departure. Light arriving at Earth from Alpha Centauri is already more than 4 years old, so the position being observed is itself delayed. The navigation problem therefore begins with a subtle fact: the spacecraft is not chasing the image in the sky. It is chasing a future physical location inferred from measurements of a past one. The faster the mission travels, the smaller the time available for the destination to move, but the more unforgiving the trajectory becomes. A slow spacecraft can make corrections over centuries, at least in principle. But a vehicle moving at a significant fraction of the speed of light covers enormous distances before small errors can be recognized and corrected. A tiny angular mistake at departure can grow into a misdistance measured in millions of kilometers by the time the craft reaches Alpha Centauri. The relationship is simple. The farther an object travels, the larger the sideways displacement created by the same pointing error. Interstellar distance turns microscopic inaccuracies into astronomical separations. This is why the phrase aiming at another star understates the problem. The spacecraft must know not only the direction of its target, but its own velocity with extraordinary precision. Any error in speed changes arrival time, and a change in arrival time changes where the target will be. A navigation mistake along the direction of travel therefore becomes linked to a navigation mistake across the sky. If the probe arrives too early or too late, Alpha Centauri may not be where the original intercept solution expected it to be. The spacecraft must continuously estimate its own position and velocity as it travels, but ordinary navigation methods become more difficult once the solar system recedes. Near Earth, spacecraft can use radio tracking from ground stations, compare their motion with well-known planetary positions, and receive frequent updates. Deep in interstellar space, Earth becomes a distant reference point. Radio signals weaken with distance, and the long communication delay makes ground control increasingly unsuitable for rapid correction. The probe will need to determine much of its trajectory independently. Stars themselves can serve as navigational references because their angular positions create a stable pattern across the sky. Pulsars, rapidly rotating neutron stars that emit highly regular pulses, have also been studied as potential natural navigation beacons. By comparing observed pulse timing and direction with stored models, a spacecraft could estimate aspects of its position without depending entirely on Earth. Optical measurements of the Sun, nearby stars, and the changing apparent position of Alpha Centauri could provide additional information. None of these techniques removes the need for precise onboard computation. The vehicle has to combine imperfect measurements, account for instrument drift, and decide whether a trajectory correction is genuinely required. Every correction has a cost. A spacecraft moving at relativistic speed cannot casually change direction. Even a small adjustment requires momentum, and momentum changes require propulsion or some other force. If the craft carries only a tiny amount of propellant for course correction, navigation errors must remain correspondingly small. A laser-driven sail probe presents a special case. Most of its acceleration may occur near the beginning of the mission, while the beam from the solar system is still able to push effectively on the sail. Once the acceleration phase ends and the vehicle enters a long coast, large later corrections become difficult. The departure trajectory therefore has to be extremely accurate. Minor steering systems might refine the path, but the mission cannot assume that a major mistake can be repaired halfway to Alpha Centauri. This places unusual importance on early measurement and guidance. The probe must leave the solar system with a velocity vector close enough to the desired intercept that decades of travel do not amplify the error beyond recovery. The chosen destination inside the system also matters. A mission aimed merely to pass through the broad neighborhood of Alpha Centauri has a much larger target than a mission meant to fly close to Proxima Centauri b. A planetary encounter demands precision on a far smaller scale. The spacecraft must first reach the correct star, then arrive at the correct time and geometry to approach a planet that is itself orbiting rapidly. Proxima Centauri b completes an orbit in only a small number of Earth days compared with the decades of the interstellar crossing. During the final phase of the mission, a timing error that seems minor on interstellar scale could determine whether the probe passes near the planet or misses it by an enormous margin. The planet's orbital position must therefore be predicted, observed, and updated as the spacecraft closes in. This becomes harder because the probe approaches at extreme speed. The final system may change from a distant unresolved point into a rapidly expanding field of separate objects over a relatively short interval. Decisions that planetary spacecraft can spread across months may need to occur much faster. The navigation system must recognize the destination, distinguish one stellar component from another, update planetary ephemerides, and adjust the observing sequence before the encounter is over. For a flyby probe, there may be no second chance. Once it passes the target, its velocity carries it onward into interstellar space. A missed pointing command could leave a camera looking in the wrong direction for the most important minutes of a mission that required decades to arrive. Navigation therefore includes more than preventing the spacecraft from missing the star system. It includes placing the vehicle in the right geometry to perform science. Instruments must know when to turn, which object to track, and how to compensate for the apparent motion produced by the probe's own immense velocity. Communication antennas may need to remain aligned with the distant solar system while sensors look toward the destination. Shielding may constrain which surfaces can face forward. Thermal systems may impose additional attitude limits as the probe approaches a brighter star. The trajectory becomes entangled with almost every other part of the spacecraft. A crewed mission would have more capability for correction, but it would also carry far more momentum. A large starship moving at a substantial fraction of light speed would need immense energy to alter its path significantly. The safest strategy would still be to make the initial intercept as accurate as possible and reserve later propulsion for small adjustments. In that sense, interstellar navigation rewards prediction over reaction. The vehicle must know where the destination is going, know how its own motion is evolving, and correct small deviations before they grow large. The long darkness between stars is therefore not a straight corridor. It is a continuously solved geometry problem in which both ends of the journey are moving. The solar system recedes, Alpha Centauri advances along its own path, and the spacecraft occupies a narrow trajectory between them that must remain accurate across trillions of kilometers. By the time the destination becomes visibly distinct enough to guide the final approach directly, most of the journey has already been determined. The deeper constraint is that navigation cannot rely on immediate help from home. At the far end of the crossing, even a perfectly detected problem cannot be reported to Earth and corrected in real time, because every command still has to cross the same 4-light-year gulf the spacecraft has just survived. At the distance of Alpha Centauri, communication stops behaving like conversation. A radio signal or a laser transmission cannot move faster than light, so even under ideal conditions, a message sent from Earth toward Proxima Centauri would need a little more than 4 years to arrive. A reply would require a little more than 4 years to return. The simplest question and answer could therefore span more than 8 years. Nothing about better antennas, faster computers, or more powerful transmitters can remove that delay, because the limit belongs to the structure of space itself. A spacecraft near another star may remain connected to Earth, but it cannot remain remotely controlled in the familiar sense. By the time mission controllers learn that something has happened, the spacecraft has already spent years living with the consequences. By the time a corrective instruction arrives, the situation that produced the problem may be nearly a decade old from the perspective of the people who first received the report. This turns autonomy from a useful feature into one of the defining requirements of interstellar flight. Present spacecraft already operate with a degree of independence because communication delays exist throughout the solar system. A probe near Mars may wait minutes for a signal. A spacecraft near the outer planets may face delays measured in hours. During critical events, onboard computers execute stored commands because there is no possibility of immediate human intervention. Interstellar missions extend the same principle until the ground can no longer participate in moment-to-moment decisions at all. A probe approaching Alpha Centauri must recognize hazards, update its navigation, choose observing sequences, protect damaged systems, and decide how to use limited power without waiting for Earth to approve each step. The software is not merely carrying out a long list of instructions prepared before launch. It has to interpret conditions that cannot be known completely in advance. That requirement begins long before arrival. During the cruise between stars, the spacecraft must monitor its own health. Radiation may corrupt memory or damage electronics. Dust impacts may weaken sensors or alter the attitude of the craft. Power output may decline. Thermal systems may drift. Communication equipment may lose efficiency. A failure discovered by onboard diagnostics cannot simply be reported and left unresolved until engineers respond. The spacecraft must identify which subsystem is affected, determine whether the readings are trustworthy, isolate the fault, and select a safe operating state. If redundant hardware exists, it may need to switch automatically. If a sensor becomes unreliable, the navigation software may have to estimate position using other references. If power falls below expectation, scientific systems may need to shut down while essential functions remain active. Each decision has to be made with enough caution to avoid turning a minor anomaly into a larger failure. This is more difficult than ordinary automation because interstellar missions last for decades and encounter conditions that may not match the assumptions built into the original software. A system written many years earlier has to remain useful after components have aged and after the destination has been observed with far greater detail than was available at launch. The spacecraft therefore benefits from flexibility rather than a rigid script. It may carry models that can be updated, planning software that can evaluate different courses of action, and learning systems able to classify unfamiliar observations. Yet autonomy introduces its own risks. A machine capable of making decisions can also make incorrect decisions. Software bugs, damaged sensors, misleading data, or incomplete models can cause the spacecraft to choose a response that engineers on Earth would reject if they were present. For that reason, autonomy cannot simply mean giving the vehicle unrestricted freedom. It has to be designed around boundaries, priorities, and methods for checking uncertain conclusions. The spacecraft needs to know which functions are essential, which can be sacrificed, and which decisions are too dangerous to make without multiple independent confirmations. A navigation correction, for example, may require agreement between several sensors before propellant is spent. A shutdown of a major power system may require evidence that continued operation poses a greater risk. The vehicle becomes less like a remotely piloted machine and more like an isolated observatory with its own operating discipline. Arrival at Alpha Centauri makes the communication problem even sharper because the most valuable scientific opportunities may unfold quickly. A high-speed flyby probe could pass through the most important observing geometry in hours or days. Earth cannot watch the encounter unfold and redirect the cameras in response. By the time the first close-range images arrive in the solar system, the spacecraft may already be far beyond the target. Every observation made during the encounter must therefore depend on onboard recognition and planning. The probe may need to distinguish stars from planets, identify cloud structures, detect unexpected rings or moons, adjust exposure times, prioritize unusual spectra, and decide which measurements deserve the most storage. If the mission is aimed at Proxima Centauri, the planet may not appear exactly as expected. Its atmosphere could be denser, thinner, cloudier, or absent. The visible hemisphere at closest approach may contain features no model predicted. Instruments must be able to respond to what is actually present rather than only to what planners imagined decades earlier. Data handling becomes part of the same autonomy problem because the spacecraft may collect information far faster than it can send it home. Communication across several light years is difficult not only because of delay, but because signals spread and weaken with distance. A tiny probe has limited electrical power and a small transmitting system. Even a larger spacecraft cannot assume unlimited bandwidth. The vehicle may therefore need to compress data, discard low-value measurements, and preserve the most scientifically important observations for transmission over months or years. That selection has consequences. Once raw information is deleted, it may never be recovered. An autonomous system must decide what matters before scientists on Earth have seen the full context. The safest approach may be to keep multiple levels of data where possible, retaining summaries, selected raw samples, and diagnostic records so that later interpretation does not depend entirely on an onboard judgment made during a brief encounter. Communication also becomes increasingly fragile as the probe recedes from the Sun. Pointing accuracy matters because a narrow beam can carry information more efficiently, but it must be aimed toward a solar system that is itself moving across the probe's sky. A small error in antenna or laser orientation can reduce the signal sharply. The spacecraft may need to alternate between observing the destination and pointing communication equipment toward Earth, unless separate systems allow both at once. It must also know when Earth-based receiving facilities are likely to be available. Although schedules created before launch may become outdated over decades, a sufficiently capable mission could carry updated communication plans received during cruise. But those updates always arrive years after being sent once the probe is near its destination. The relationship between Earth and spacecraft becomes asynchronous. Ground controllers are not commanding the present. They are sending advice to a future spacecraft based on information from its past. That temporal separation changes the human side of the mission as well. Teams that launch the probe may not be the same teams that receive its encounter data. Institutions must preserve technical knowledge across generations of engineers and scientists. Documentation must remain understandable. Communication standards must remain supported. Receivers capable of detecting the distant signal must still exist and know where and when to listen. This spacecraft may be functioning perfectly while the civilization behind it changes languages, technologies, organizations, and scientific priorities. Maintaining contact, therefore, becomes partly an engineering problem on Earth. The mission needs continuity at both ends of the link. For a crewed starship, the delay is even more profound. The people aboard could exchange messages with Earth, but not conversations in real time. A personal transmission sent near Alpha Centauri would reach home years later, and any response would return years after that. Operationally, the crew would have to govern its own ship, make medical decisions, repair systems, manage emergencies, and resolve conflicts without immediate assistance from the planet of origin. Earth could provide knowledge, long-term guidance, and updated scientific information, but it could not act as mission control in the traditional sense. The further the ship travels, the more independent its society must become. The communication link remains emotionally and scientifically important, yet it cannot remove isolation. This is the deeper meaning of a 4 light-year delay. Distance does not merely slow information, it separates cause from response so completely that control has to move on board the spacecraft. Navigation, engineering, science, and survival all become local responsibilities. Earth can observe only after the fact and advise only for the future. By the time the first detailed data from Alpha Centauri reaches the solar system, the spacecraft that gathered it has already moved on from the moment being described. If the mission is a fast flyby, it may be millions or billions of kilometers beyond the system before humans even know whether the closest approach succeeded. Autonomy can keep the mission alive through that silence, but it cannot solve the final mechanical problem waiting at the destination. A spacecraft that reaches Alpha Centauri at interstellar velocity still carries all the momentum that made the crossing possible, and unless some way exists to remove it, the vehicle will have only the briefest encounter before the stars begin receding behind it. Arrival sounds like the natural end of a journey, but for an interstellar spacecraft it may be only another name for passing through. A probe approaching Alpha Centauri at a significant fraction of the speed of light carries the same enormous kinetic energy that made the crossing possible. And unless that energy is removed, the spacecraft cannot remain near the system. It does not simply reach the destination and stop. It enters the region at thousands or tens of thousands of kilometers per second and continues onward. For a fast flyby mission, that may be acceptable. The spacecraft can gather observations during the brief interval when the stars and planets are close enough to study in detail, then continue into interstellar space. For any mission intended to orbit, linger, or eventually support human exploration, however, the vehicle has to slow down, and slowing down can be almost as difficult as speeding up. The basic physics is unavoidable. Velocity is not lost merely because the target has been reached. A spacecraft moving at 1/5 of the speed of light relative to Alpha Centauri will still be moving at roughly that speed unless some force acts against its motion. The energy stored in that motion is immense. To remove it using onboard propulsion, the spacecraft must generate thrust opposite its direction of travel for long enough to reduce the velocity to something compatible with the target system. If the same propulsion method is used for braking that was used for acceleration, the mission may effectively need a second large energy budget at the far end. For a rocket carrying its own fuel, this creates a severe mass penalty. The propellant reserved for deceleration has to be carried throughout the entire journey. That means it must first be accelerated along with the spacecraft, increasing the energy required at departure. The fuel needed for arrival becomes part of the burden of leaving. This is one reason interstellar concepts become so sensitive to mission architecture. A flyby can discard almost the entire braking problem. The spacecraft invests its energy in reaching a high cruise speed and accepts that it will never stop. An orbital mission cannot. It must carry or acquire some means of shedding velocity after crossing several light years. The difference may determine whether a mission remains technologically imaginable or becomes overwhelmingly difficult. The scale of the encounter itself also changes with speed. Alpha Centauri is a stellar system, not a compact destination like a space station. Its important targets may be separated by vast distances, yet a high-speed probe can cross those distances surprisingly quickly. At relativistic velocity, the period during which a nearby planet is large in the instruments may be measured in hours rather than months. The stars can move from distant points to major sources of heat and radiation, and then recede again over a very compressed interval. Scientific instruments must be prepared in advance because there is no time to improvise from Earth. A flyby can still return extraordinary science, but it trades depth for speed. There may be no opportunity to circle a planet repeatedly, observe changing weather, map seasonal variations, or study a moon from different angles. The entire mission may depend on a narrow path through the system and a short sequence of observations. Slowing down would change everything. A spacecraft that could reduce its velocity and remain near Proxima Centauri, Alpha Centauri A, or Alpha Centauri B could study the local environment for years. It could map planets over repeated orbits, observe stellar activity over time, search for smaller bodies, and perhaps adjust its course toward additional targets. The scientific value could be vastly greater. The energetic cost of gaining that time is the problem. Traditional braking with a rocket means carrying reaction mass. Nuclear propulsion concepts may improve performance, but they do not eliminate the need to change momentum. Antimatter could in principle provide extremely high energy density, yet producing, storing, and controlling enough of it remains far beyond current capability. Fusion concepts face their own challenges in reactor mass, fuel handling, heat rejection, and long-term reliability. Every braking engine is also equipment that has to survive the entire interstellar crossing before it is needed most. A component that fails shortly after launch may be detected. A component that quietly degrades over decades could remain apparently healthy until the moment the spacecraft attempts to slow down, when failure would convert an orbital mission into an unintended flyby. This has encouraged interest in methods that use the destination environment itself. A light sail pushed away from the solar system by a powerful beam might, in principle, use pressure from the destination star to reduce speed if the sail can be oriented and controlled correctly. Stellar photons carry momentum, and a sufficiently large reflective sail can exchange momentum with that radiation. The difficulty is that the available pressure is limited and depends strongly on distance from the star. A probe approaching quickly has little time to make use of the strongest radiation field unless it passes very close to the star, where heating and navigation become more severe. The trajectory would have to be designed so that the sail survives the encounter while extracting enough momentum change to matter. Another family of ideas uses magnetic fields rather than light. A magnetic sail could interact with charged particles in the stellar wind or the interstellar medium, using an extended magnetic field as a kind of invisible braking surface. In principle, this allows a spacecraft to exchange momentum with surrounding plasma without carrying all of its braking propellant. But the surrounding material is extremely thin, so the system may require enormous effective area and long braking distances. The magnetic field would also need to be generated by equipment that adds mass and consumes power. These concepts are attractive because they try to turn the destination environment into part of the propulsion system. But they remain difficult engineering problems rather than established solutions. Gravitational braking provides another possibility in certain geometries. A spacecraft can use a close passage near a star to change its direction and speed relative to other bodies. Just as probes in the solar system use planets for gravity assists. But gravity does not simply erase kinetic energy in the reference frame that matters. To become bound to a system, the vehicle still has to lose enough energy relative to the target. Clever trajectories involving multiple stars may help redistribute momentum, especially in a binary system like Alpha Centauri A and B, but they demand extraordinary precision and may require dangerously close approaches to luminous stars. For a human mission, the braking problem becomes even less forgiving. A crewed vehicle is likely to be massive because of shielding, life support, living space, reserves, and redundancy. That mass must be accelerated on departure and then decelerated on arrival. If the braking phase is too intense, the crew experiences high acceleration. If it is gentle, it may need to begin far from the target and continue for months or years. The entire mission timeline changes. A voyage advertised as a few decades at high cruise speed might require significant additional time for comfortable acceleration and braking. The shortest possible crossing is therefore not necessarily the most practical journey. Human tolerance, engine performance, fuel economy, thermal limits, and mission safety all shape the velocity profile. Even robotic missions face similar trade-offs. A tiny probe can be made fast precisely because it carries very little. Adding a braking system can erase that advantage. A sail large enough to accelerate efficiently may be difficult to preserve for decades. A magnetic system may weigh more than the instruments it is meant to deliver. A fuel reserve may dominate the spacecraft mass. This is why many realistic early interstellar concepts focus on flybys. A flyby accepts a scientific compromise in exchange for a major reduction in propulsion complexity. The spacecraft arrives, observes, and leaves. It may never again approach a star or planet closely. The first images of another stellar system could therefore be gathered by a machine that is already escaping from that system at almost the same moment the images are taken. There is something revealing in this. The greatest challenge of interstellar travel is not simply reaching the distance, it is controlling motion across that distance. A spacecraft slow enough to stop easily takes too long to arrive. A spacecraft fast enough to arrive within decades becomes difficult to stop. The useful mission lies between those constraints. Alpha Centauri therefore turns arrival into an engineering decision rather than a finish line. A probe must be designed from the beginning around whether it intends to pass through or stay. The choice determines propulsion, mass, shielding, navigation, observation strategy, and power. If it stays, the vehicle gains time but pays for that time in energy and complexity. If it does not, the entire encounter may last only a small fraction of the journey that preceded it, and even after this decision is solved, there remains another question that cannot be avoided: where exactly within Alpha Centauri should the spacecraft attempt to go? Because the nearest stellar system is not one destination but three very different stars. Alpha Centauri is not a single star waiting at the end of the journey. It is a system of three suns arranged on very different scales, and that structure changes what arrival actually means. Alpha Centauri A and Alpha Centauri B form the bright central pair, two stars bound in a long mutual orbit around a shared centre of mass. Proxima Centauri, much fainter and much smaller, lies far from them and follows a vastly wider path around the system. From Earth, all three belong to the nearest stellar neighbourhood, but a spacecraft approaching after decades of flight cannot treat them as one compact destination. The separation between the central pair and Proxima is large enough that choosing one target means committing to a very different arrival geometry, radiation environment, scientific program, and possibly braking strategy. The mission must therefore decide long before launch what the phrase Alpha Centauri is supposed to mean in practice. Alpha Centauri A is the most sun-like of the three. It is somewhat larger and brighter than the Sun, with a surface temperature and spectral character that make it immediately interesting as a nearby analogue to the kind of star around which Earth evolved. Alpha Centauri B is slightly smaller and cooler, yet still belongs to the same broad class of ordinary hydrogen-burning stars. The two orbit one another over a period measured in decades, alternately drawing closer and moving farther apart. Their changing separation means the gravitational environment around each star is not equivalent to the relatively isolated architecture of the solar system. Any planets orbiting either member of the pair would exist inside a system where a second star periodically changes position and distance in the sky, adding a long-term gravitational influence that can affect orbital stability. Stable planetary orbits are still possible around either star, but the region in which they can survive must be understood in the context of the binary. A spacecraft aimed at the central pair would therefore arrive not at one gravitational centre, but inside a moving two-star system whose geometry has been evolving throughout the entire interstellar crossing. That motion matters for navigation as well as science. The position of Alpha Centauri A relative to Alpha Centauri B changes noticeably over time, so a probe cannot simply target a fixed midpoint and decide at the end which star to investigate. A close flyby requires a precise approach corridor. Passing near one star may place the other millions or billions of kilometers away, depending on the orbital phase at arrival. At interstellar velocity, that separation may be too great to cross afterward without a major course change. A mission designed around Alpha Centauri A would need an intercept optimized for that star. A mission designed around Alpha Centauri B would require a different one. Even a probe capable of some maneuvering might be unable to explore both closely unless its trajectory was planned around the binary structure from the beginning. Proxima Centauri presents an even stronger contrast. It is a red dwarf, much smaller, cooler, and dimmer than either Alpha Centauri A or B. Despite being the closest individual star to the Sun, Proxima is not close to the central pair in ordinary planetary terms. It lies thousands of times farther from Alpha Centauri A and B than Earth lies from the Sun. The orbit connecting Proxima gravitationally to the brighter pair is therefore enormous, with estimates placing its period at more than 500,000 years. On the scale of human history, Proxima hardly seems to move around the central pair at all. On the scale of stellar dynamics, however, it belongs to the same system. This wide architecture is one reason the phrase triple star can be misleading if it creates an image of three suns crowded together. Alpha Centauri A and B form a comparatively close binary, while Proxima occupies a remote outer position, more like a distant companion travelling around the pair on a path so large that a single orbit spans a significant fraction of the time modern humans have existed. For an interstellar spacecraft, the practical result is clear. Reaching Proxima Centauri does not mean the central pair is conveniently nearby. A probe that performs a fast flyby of Proxima would not simply continue for a short time and then inspect Alpha Centauri A and B at close range. The additional distance is substantial, and at high velocity the required change in direction could be difficult or impossible without dedicated propulsion. A mission to the central binary and a mission to Proxima are therefore almost separate interstellar missions that happen to share the same broad destination name. Their scientific motivations would also differ. Alpha Centauri A and B are attractive because they offer nearby examples of stars more similar to the Sun. If planets exist in stable orbits around either star, they would provide a rare opportunity to compare planetary systems formed in a binary environment with the solitary arrangement around the Sun. The presence of a stellar companion could have influenced the distribution of material in the original protoplanetary disks, the migration of planets, the delivery of comets and asteroids, and the long-term stability of any temperate worlds. Observing such a system at close range could help distinguish which features of the solar system are common and which depend on the Sun having formed without a nearby stellar companion that remained bound. Proxima is interesting for a different reason. Its importance is strengthened by the known presence of at least one planet in a close orbit, making it not merely the closest star but the location of the nearest known exoplanet of particular interest. Yet the star itself is far less sun-like. Red dwarfs are cool and faint, so planets receiving Earth-like amounts of stellar energy must orbit much closer to them than Earth orbits the Sun. That compact scale creates a different planetary environment from anything in the solar system. The star's magnetic activity, flare behavior, particle output, and long-term luminosity history can become central to whether a nearby planet retains an atmosphere or maintains conditions compatible with liquid water. Choosing Proxima as the mission target therefore directs the scientific emphasis toward the relationship between a small active star and a tightly orbiting planet. Choosing Alpha Centauri A or B shifts the emphasis toward more sun-like stars and the architecture of planets in a binary. The stellar environments also affect spacecraft engineering during arrival. A probe approaching one of the brighter stars encounters a stronger radiation field as it closes in, which may be useful if a light sail attempts to use stellar photons for braking. The same radiation also produces thermal stress and constrains how close delicate instruments can safely pass. Proxima is much dimmer, reducing the available photon pressure for sail-based deceleration and changing the thermal environment. Yet its magnetic activity and flares create a different hazard. A vehicle designed to survive near one target may therefore not be ideal for another. Even the timing of observations differs. A probe passing through the central binary must account for two bright stars and the changing gravitational geometry between them. A probe approaching Proxima may concentrate more heavily on its compact planetary region, where orbital periods are short and the relevant distances are much smaller. The system forces mission planners to define success precisely. A vague objective of reaching Alpha Centauri is not enough. Does success mean passing through the gravitational neighborhood of the triple system? Photographing one of the bright stars? Searching for planets around the binary? Flying close to Proxima Centauri B? Or slowing down enough to remain for extended observation? Each goal selects a different trajectory and imposes a different balance of propulsion, shielding, autonomy, and navigation. The decision may even affect departure from the solar system, because the spacecraft must be accelerated onto a path that anticipates the future position of the chosen stellar component decades later. Once travelling at relativistic speed, changing that choice is not simple. There is a deeper lesson in the architecture of the system. Interstellar travel is often imagined as movement from one point to another, from the Sun to Alpha Centauri, as if stars occupy isolated dots on a map. A real stellar system is a moving gravitational landscape. Its components orbit, its planets move, its radiation fields vary, and its most interesting targets may be separated by distances that are themselves large enough to dominate mission design. Even the nearest system contains complexity before any unknown planet or moon is discovered. The journey across 4 light years does not end at a single doorstep. It ends at a set of choices. Alpha Centauri. A offers one environment, Alpha Centauri B another, and Proxima Centauri another still. The closest of the three is also the smallest and most active, while the stars most similar to the Sun belong to a binary whose internal motion must be respected by any arriving spacecraft. The destination is therefore not merely nearer or farther, safer or more dangerous, it is structurally divided. And among those 3 possible targets, one world in particular gives Proxima a powerful claim on the first interstellar mission. Because orbiting close to that faint red star is the nearest known planet that might, under the right conditions, allow liquid water to exist. Proxima Centauri b gives the journey its most obvious scientific destination, because it orbits the nearest star to the Sun and lies at a distance from that star where liquid water could, under suitable conditions, exist on the surface. The planet completes an orbit in about 11.2 days, a period so short that its entire year would pass before Earth has moved far through a single month. That rapid orbit is a direct consequence of Proxima Centauri itself. The star is a red dwarf, much smaller and dimmer than the Sun, so a planet does not need to orbit at anything like Earth's distance to receive a comparable amount of stellar energy. Proxima Centauri b travels much closer to its star, inside the region commonly described as the habitable zone, where temperature conditions may allow liquid water if the planet possesses the right atmosphere and surface environment. The phrase is useful, but it is also easy to misunderstand. A habitable zone is not a declaration that a planet is habitable. It marks only a range of distances where stellar heating is compatible with one necessary condition for surface water. Everything else remains open. The planet may have a thick atmosphere, a thin one, or almost none at all. Its surface pressure may be suitable for stable water, or it may force water to freeze, boil, or disappear into the subsurface. Its atmosphere may contain gases that trap enough heat to moderate the climate, or it may have been eroded over time. The planet may be dry, ocean-covered, geologically active, magnetically protected, or exposed. Distance from the star is only the first filter, and Proxima Centauri b passes that filter without settling any of the larger questions. The difficulty begins with the nature of the star. Red dwarfs can remain active for immense spans of time, and Proxima Centauri is known for powerful flares. During a flare, magnetic energy stored in the star's atmosphere is released rapidly, increasing emission across several wavelengths and sending energetic particles outward. A planet orbiting close to such a star experiences these events from a distance far smaller than the separation between Earth and the Sun. The consequences depend on the planet's atmosphere, magnetic field, and the frequency and strength of the stellar activity, but the concern is straightforward. Repeated energetic radiation can alter atmospheric chemistry. Charged particles can interact with the upper atmosphere and, under some conditions, help strip gases away over long periods. Ultraviolet and higher energy radiation can damage complex molecules at the surface. A world can therefore occupy the correct temperature zone while still existing inside an environment that makes stable surface habitability difficult. This does not prove that Proxima Centauri b is sterile. It means the concept of habitability has to include the history of the star as well as the present orbit of the planet. Red dwarfs also evolve differently from stars like the Sun. Early in their lives, they can remain more luminous relative to their later stable state than their small present appearance might suggest. A planet that now lies in a temperate zone may have spent an earlier period receiving far more energy. If Proxima Centauri b formed with substantial water, an extended hot phase could have driven strong evaporation. Water vapor reaching the upper atmosphere can be broken apart by energetic radiation, allowing hydrogen to escape more easily into space over long time scales. This process could reduce a planet's original water inventory. The uncertainty is substantial because the starting conditions are unknown. A planet may begin with far more water than Earth. It may receive additional volatiles later. Its interior may release gases through volcanism. A sufficiently massive atmosphere may survive erosion that would remove a thinner one. This is why an interstellar probe would be valuable. From Earth, Proxima Centauri b is not seen as a resolved world with continents, clouds, and weather. Its existence is inferred from the effect it has on the motion of its star, and many of the properties most important to habitability remain difficult to measure. The planet's atmosphere, if one exists, is one of the central unknowns. Detecting gases around a world so close to a faint but active star is technically demanding. Stellar variability can complicate the signal. Clouds and hazes can hide deeper atmospheric layers. A lack of easy detection does not necessarily mean a lack of atmosphere. A close spacecraft encounter would transform the problem by gathering information from a distance impossible for Earth-based telescopes to match. Images could constrain surface brightness patterns and cloud cover. Spectrometers could search for atmospheric gases and measure how they change across the planet. Instruments could characterize particles and magnetic fields around the star. Even a fast flyby could connect stellar behavior with planetary conditions in a way remote observations cannot easily reproduce. The most important result might not be a simple answer about life. It might be a more basic determination of what kind of world Proxima Centauri b actually is. If a substantial atmosphere surrounds it, that would immediately sharpen models of atmospheric survival around active red dwarfs. If the atmosphere is extremely thin or absent, the result would place strong constraints on how vulnerable close-orbiting planets can be. If water-related features or signs of a temperate climate were detected, the planet would become a far more compelling target for later missions. If the surface appeared dry and heavily irradiated, the nearest potentially temperate exoplanet would instead become a warning about the limits of the habitable zone concept. Their small size and low brightness make nearby planets easier to detect than similar planets around stars like the Sun, and many known rocky planets orbit them at close distances. Proxima Centauri b is therefore not only one nearby world, it is a test case for an entire category of planetary environments. If planets around active red dwarfs can preserve atmospheres and stable surface water, then the number of places where temperate conditions might exist could be enormous. If their atmospheres are usually stripped or their surfaces repeatedly sterilized, the galactic landscape of potentially habitable planets would look very different. The journey to the nearest star would then be answering a question with consequences far beyond the Alpha Centauri system. There is also the possibility that habitability, if it exists, may not resemble Earth closely. A planet in such a tight orbit may experience strong tidal effects from its star. One possible outcome is a rotation state in which the same side remains directed toward the star for long periods or permanently. that does not automatically make the world uninhabitable. A substantial atmosphere or ocean can transport heat from the illuminated side toward the darker side, reducing temperature extremes. Clouds can alter how much stellar energy is reflected back into space. The boundary between permanent day and permanent night could support conditions different from either hemisphere. Without direct knowledge of the atmosphere and circulation, simple pictures of one burning side and one frozen side remain too crude. The planet may be harsher than expected, but it may also possess climate mechanisms that are difficult to infer from orbit alone. These possibilities make the destination scientifically rich while leaving the emotional logic of the voyage strangely unresolved. A civilization capable of crossing 4 light-years would not be travelling toward a confirmed second Earth. It would be travelling toward uncertainty. The world at the end may have no breathable air, no open oceans, and no surface conditions suitable for human life. It may have retained an atmosphere but lost most of its water. It may be geologically inactive. It may be wrapped in clouds that conceal the surface. It may prove far more temperate than current evidence can establish. The mission would have to justify its enormous energy, risk, duration, and complexity without knowing which of these possibilities is waiting. That is part of what makes Proxima Centauri b such a powerful destination. Its importance does not depend on it being Earth-like. Its importance comes from being close enough, in astronomical terms, to become the first rocky world around another star that a future interstellar probe could plausibly examine at intimate range. The 4 light-year gulf would still demand propulsion far beyond ordinary spacecraft, protection from dust and radiation, decades of autonomous operation, precise navigation, delayed communication, and perhaps a braking system capable of removing an extraordinary amount of kinetic energy. After all of that, the reward may be a planet that turns out to be barren. Yet even barrenness would answer questions that cannot be settled from a distance. It would reveal how atmosphere, stellar activity, orbital geometry, and planetary history combine around the most common type of star in the galaxy. Alpha Centauri is the nearest stellar system, but proximity does not make the journey easy, and a potentially temperate planet does not guarantee a welcoming destination. The deeper paradox is that the first interstellar voyage may require one of the greatest engineering efforts. A technological civilization can attempt merely to learn whether the nearest promising world can keep an atmosphere, hold liquid water, and remain stable beneath an active red sun. 4 light-years is close enough to tempt exploration, and far enough to turn that exploration into a test of almost every limit the spacecraft carries with it. The distance to Alpha Centauri remains small only when measured against the galaxy, against the scale of machines, lifetimes, energy, and survival. It becomes something far more demanding. The journey begins inside the familiar boundaries of the solar system, passes beyond the heliosphere, and then enters a region where every ordinary assumption about travel becomes less useful. Speed must increase by extraordinary amounts, yet greater speed creates new hazards. Dust becomes destructive, radiation accumulates, navigation becomes less forgiving. Communication separates action from response by years. Every system must endure without rescue, and every kilogram added for protection, repair, or survival makes acceleration more difficult. Even arrival refuses to become simple. A spacecraft fast enough to cross the distance within decades may reach the destination only to discover that stopping requires another immense act of engineering. Beyond that problem waits a system divided among 3 very different stars, and around the nearest of them, a planet whose position in the habitable zone offers possibility without certainty. Proxima Centauri b may have an atmosphere, or it may have lost much of what once surrounded it. It may preserve water, or it may reveal how difficult survival can be around an active red dwarf. The answer remains unknown because the gulf is still too large for direct exploration. That uncertainty is not a weakness in the story. It is the reason the journey matters. The nearer stars are close enough to study, close enough to imagine reaching, and still distant enough to expose the full scale of the challenge. Alpha Centauri stands at the edge of what feels almost possible, a reminder that the first step beyond the solar system may not begin with a dramatic leap, but with a slow accumulation of solutions to problems that space has been quietly holding in place for billions of years.